Hey everyone, and welcome back. Have you ever paused to think about how absolutely wild it is that we can remember things? Like, what you had for breakfast, or the name of your best friend, or that embarrassing thing you did in third grade? Our brains are constantly creating and storing memories, and it's a process so intricate and fascinating, you might just be surprised. Today, we're diving deep into the brain's ultimate memory architect, the hippocampus. It's a small but mighty structure that's central to how we form new memories. Let's get into it. First things first, where is this amazing hippocampus located? Well, if you could peek inside your head, you'd find two of them, one in each hemisphere of your brain. They're tucked deep within your temporal lobe, and they're shaped kind of like a seahorse, which is actually where they get their name from. Hippocampus comes from the Greek words for horse and sea monster. So, picture a little seahorse chilling out in the middle of your brain. Pretty cool, right? This isn't just a random spot, its location is super important for how it connects with other brain regions. Before we get into the how, let's quickly define what. When we talk about memory in this context, we're focusing mostly on what scientists call declarative or explicit memory. This is the kind of memory you can consciously recall and talk about. Think of it as knowing that something happened. It's different from implicit memory, like knowing how to ride a bike, which is more about skills and habits. Declarative memory is our focus today because it's where the hippocampus truly shines. Even within declarative memory, we've got a couple of categories. We have episodic memory, which is your memory of specific events and experiences, complete with time and place. Like your 10th birthday party, or what you ate for dinner last night. Then there's semantic memory, which is your general knowledge about the world, facts, concepts, and ideas. For example, knowing that Paris is the capital of France, or what a neuron is. The hippocampus is vital for forming both these types of memories. So, here's a crucial point: the hippocampus doesn't actually store your long-term memories forever. Think of it more as a temporary processing center, a kind of staging area. It's like the gatekeeper or the librarian who helps you catalog new books. When new information comes in, the hippocampus works to organize and stabilize it, preparing it for eventual long-term storage elsewhere in your brain, mainly in the neocortex. It's a temporary holding zone, which is a really important distinction. Without it, new memories can't even get past the front door. How does information even get to the hippocampus in the first place? Well, it all starts with your senses. Everything you see, hear, smell, taste, and touch generates electrical signals. These signals travel through various brain regions, like the sensory cortices, and eventually converge in an area called the entorhinal cortex. Think of the entorhinal cortex as the hippocampus's main entry point, the grand foyer where all sensory data arrives before being presented to the memory manager. This is where the magic really begins. Once the information hits the entorhinal cortex, it then makes its way into the hippocampus itself, following very specific neural pathways. This initial processing is what we call encoding, the brain's way of transforming sensory information into a memory trace. It's not just a passive recording. The hippocampus is actively working to make sense of this new data, associating different pieces of information together. Imagine it like creating a basic draft of a story, linking characters, settings, and initial plot points. This first pass is crucial for laying the groundwork. So, how does the hippocampus actually change to form these memory traces? The answer lies in something called synaptic plasticity. Synapses are the tiny junctions between neurons where signals are transmitted. When we learn or experience something new, the connections at these synapses can actually get stronger or weaker. Think of it like a well-worn path in a forest. The more you walk it, the clearer and easier it becomes to traverse. This ability of synapses to change their strength is the fundamental mechanism of learning and memory in your brain. It's absolutely essential. The most famous example of synaptic plasticity, especially relevant to the hippocampus, is long-term potentiation, or LTP. This is basically a persistent strengthening of synapses based on recent patterns of activity. Imagine two neurons, A and B. If neuron A repeatedly fires and successfully activates neuron B, the connection between them gets stronger and more efficient. It's like a neurons that fire together, wire together principle. This strengthened connection makes it easier for neuron B to fire in response to neuron A in the future, forming the physical basis of a memory. How does LTP actually happen at a molecular level? It's pretty complex, but at its core, it involves specific types of receptors on the surface of neurons, particularly NMDA receptors and AMPA receptors. When neurons are repeatedly activated together, calcium ions flood into the postsynaptic neuron through these NMDA receptors. This influx of calcium triggers a cascade of events, leading to more AMPA receptors being inserted into the synapse. More AMPA receptors mean the synapse becomes more sensitive and stronger. This tiny molecular dance is literally how your brain learns. This mechanism of LTP helps explain why repetition is so effective for learning. Every time you review information, practice a skill, or recall an event, you're essentially reactivating those neural pathways in your hippocampus and other brain regions. This repeated activation further strengthens the synaptic connections through LTP. So, if you're trying to learn something new for a test, or master a piece of music, doing it over and over isn't just about practicing, it's physically rewiring your brain to make those memories more robust and easier to retrieve. Consistency is key. Alright, so the hippocampus has encoded this new information and started strengthening the connections. But remember, it's not where long-term memories are permanently stored. That's where memory consolidation comes in. This is the process where unstable, newly formed memories are gradually transferred from the hippocampus to more stable, long-term storage sites in the neocortex, the outer wrinkled layer of your brain. Think of the hippocampus as a temporary factory assembling a new product, and the neocortex as the warehouse where it eventually gets filed away for good. This process takes time, sometimes days, weeks, or even years. And guess what plays a huge, almost magical role in memory consolidation? Sleep. While you're catching those Z's, your brain isn't just resting. It's actively replaying and reorganizing the day's events. The hippocampus replays patterns of neural activity that occurred during wakefulness, sending these signals to the neocortex. This replay strengthens the connections within the neocortex, essentially solidifying those memories. It's like your brain is running a super efficient overnight shift, filing away all the important information. So, getting enough quality sleep isn't just good for your body, it's absolutely essential for your memory. Once a memory has been successfully consolidated in the neocortex, you can then retrieve it. This process involves reactivating the neural patterns associated with that memory. Interestingly, even for long-term memories, the hippocampus can still play a role in retrieval, especially for very detailed or contextual episodic memories. It helps to stitch together the different pieces of a memory scattered across the neocortex. It's like the librarian isn't just cataloging, but also helping you find those books later, especially if you need multiple books on a specific topic. So, it's involved at multiple stages. Beyond just declarative memories, the hippocampus also plays a crucial role in spatial memory and navigation. This is how you know your way around your house, or how to get to your favorite coffee shop. Scientists have discovered place cells in the hippocampus that fire when you're in a specific location, and grid cells in the entorhinal cortex that help create a mental map of your environment. This shows just how intertwined our memory of what happened is with where it happened. It's pretty mind-blowing to think your brain literally maps out the world around you. If forming memories is so intricate, what about forgetting? Why do we lose memories? Well, forgetting can happen for a few reasons. Sometimes, information just isn't encoded strongly enough in the first place, maybe because we weren't paying attention. Other times, memories simply decay over time if they're not frequently recalled, those neural pathways weakening. There's also interference, where new information can make it harder to remember old information, or vice versa. And sometimes, forgetting is actually helpful, allowing our brains to prioritize and clear out less important details. It's a natural part of the memory process. So, what happens if the hippocampus gets damaged? We learn a lot about its function from studying cases where it's impaired. Damage to the hippocampus can lead to severe memory problems, particularly affecting the ability to form new declarative memories. This condition is called anterograde amnesia. People might remember things from before the damage, but struggle to recall anything new that happens after. They literally can't create new episodes or facts about their lives. It really underscores just how critical this tiny seahorse-shaped structure is to our daily learning and remembering. One of the most famous and tragic cases is that of Henry Molaison, widely known as HM due to severe epilepsy. Parts of his hippocampus were surgically removed in 1953. While the surgery helped his epilepsy, it left him with profound anterograde amnesia. He couldn't form new long-term memories. He could have a conversation, and minutes later, completely forget it had happened. Studying HM provided incredible insights into the hippocampus's role as a memory converter, essential for turning short-term experiences into lasting memories, but not for storing the memories themselves or for implicit learning. So, from that initial sensory input, through the intricate dance of synaptic plasticity, to the overnight consolidation shift, the hippocampus is absolutely central to how we learn and remember our lives. It's not just a storage unit, it's a dynamic processing hub, constantly working to build and organize the tapestry of your experiences. Understanding this process helps us appreciate the complexity of our own minds and gives us clues on how to optimize our learning and memory, like getting enough sleep, which we just talked about. Isn't that truly amazing? And there you have it, a whirlwind tour of memory formation in the hippocampus. I hope you learned something new and now have an even greater appreciation for your incredible brain. If you found this explanation helpful, please hit that like button, subscribe for more brainy content, and let us know in the comments what other neuroscience topics you'd like us to explore. What's the most surprising thing you learned about memory today? Thanks for watching, and we'll see you in the next one.